This is Nate Allen, CTO of Pollen. I'm going to give a technical aerobiology update, things that we've recently changed and things that are up and coming. One of the major changes we've made recently is to adjust the lighting and color calibration within the devices. They were formerly calibrated in theory, but with the recent changes, we've essentially measured the output conditions from the images and worked backwards to try to reach parity between the two sensors. For the APS 330, this translates to a very small adjustment. Slight lightening you might notice, but you're not likely to notice a significant difference for that sensor. For the 400, the images are quite a bit brighter and hopefully clearer and give more data for the vision recognition system to be able to recognize them, and most importantly, again, reach parity so that the same vision profiles will match them much more closely. Part of that was additional training that we did. So with the new lighting and color configurations, we added a lot more particles to the training sets. This also should just generally improve the quality of vision, something that we're trying to do regularly anyway. We're always adding to those data sets. We also are hoping that some of these changes will improve the generalization, the resilience, and the robustness of those vision models. We have a new feature. You've probably noticed in the portal we have a new sites feature which allows you to store the data that comes in instead of just on the sensor with provisions being something of a history. This allows the data to be associated with a site. This makes it easier to provision a sensor because you just have to point it to the site. But it also improves various scenarios. If you move a sensor, the data stay with the location that the data were measured at rather than go with the sensor. And then if you were to replace a sensor, of course, you could put it in the same site and the data, the old and the new data, would remain in the same place. If you decommission or unprovision a sensor, it's of course nice to have your data still readily available, which is tied again to the site rather than to the sensor that might be difficult to get to the old data from. This is reflected in new APIs, and we will be talking more about those new APIs coming pretty soon. This also enables a new scenario we're pretty excited about. This is going to allow for multiple sensors to actually cluster together and essentially create a virtual sensor which won't measure higher signal with more sensors, but will provide more accurate data. The averages improve the quality and reduce the noise, so you get more signal to noise. And of course, this also provides a scenario where it can reduce downtime. If you have a sensor that's down for maintenance or offline, the other sensor or sensors can keep the site available. Part of that is some new user interfaces. You may have noticed the new sites user interface where you can see all of the places that you've collected or have previously provisioned sensors, and if you have one or more sensors under a given site, then you can administer those from under that site. There's also a new analytics user interface. The analysis tab under the devices, under sites we're calling metrics, just to distinguish it. There are going to be some changes to the user interface, some additional features that we're going to be able to add, and I'll be talking a little bit more about what those are and what's enabled by the new way that we calculate analytics. One thing you may notice right away is that the magnitudes are significantly different. the numbers are likely to be much more comparable to what you would get from a rotorod or Burkhardt, the legacy mechanisms for counting particulates. So hopefully that will make it easier. We do still have the scale drop down, so you can change scales if you want to play around with that. Okay, so let's dive a little bit more deeply into how these are computed. One major change has to do with the way frames are put into hour blocks. In the old system, the end time of the sampling, which is typically 15, maybe 20 minutes of sampling time that a given frame, that's what's going to become a frame, is under the nozzle being collected against. The end time of that frame is associated with one given hour, and the full accounting in this example of this entire frame would all go into the, in this case, 11 o'clock hour, even though this frame technically spanned into a previous hour. Now the assumption was that that sort of washes out as you traverse across time, and but there are reasons to maybe subdivide the frame and prorate them, and so that's what we've done. So in the new system, we prorate proportionally, and we'll account for those particles fractionally if necessary towards one or the other hour. And this is done at the sort of raw count level. So if you counted, say, 3 Fraxinus particles overall in that frame, then that 3 will be divided by the proportion that goes into each hour. This is the most significant change, though, and has to do with the way that we actually account for frames overall. The assumption underlying the analytics, our old analytics, is entirely based on the presumption that the device is essentially steadily operating for the entire time period. So if you have essentially a fairly steady or constant frame rate, and it's over the entire period, so the entire, if you're looking at a month average, for instance, the entire month's period, or if you're looking at an hour over the hour period, if you have a steady rate of those, then that's what it's designed to handle. But if you don't, such as in this example of 4 frames in the 10 o'clock hour, 1 in the 11, and then 1 in the 12, because this frame will go into the 12 o'clock hour, then you'll actually notice a difference in the measurement levels in each of these hours. Whereas the new system treats each frame as a discrete sampling period. And as I mentioned with the proration, then each frame or fraction of a frame is treated as an independent event. And that's fundamentally what allows us to do the clustering that I mentioned. So it doesn't matter how many frames come in from which devices, they're improving the amount of signal that you have and increasing the accuracy of the averages, not increasing the magnitude. So this is particularly pronounced when you have periods of time where the sampler is not operational over that entire time. So you may have noticed, for instance, that if you started up a sampler near the end of a month, then the overall average for the month in the analytics would be very low, because it's again assuming that frames it starts at a very, very low number, and then assuming that frames come in over that entire period, that will determine the ability for it to fill out that time period. So now if you were to start it up at the end of a month, then the few frames that you collect at the end of the month would become the average for that month. And this may seem like it doesn't provide much accuracy because you only have a few frames that you're averaging over for the full month. But that's where we have a new output, which is the confidence factor. So we now have a confidence that comes out at the end, which gives us both a sense of the confidence coming from the vision system, but also captures this notion of how strong the signal is, essentially, within that period. So just to break this down a little bit, as far as how the concentrations are computed, the output from the vision is a set of tag categories. Those are each of the boxes that you see in the detector frames. And each of those has a confidence, its own probability. And then we now maintain a tag size histogram. So it's a 1 to 100 micron at a 1 micron resolution size histogram. So you could think of that as a PM1, PM2, all the way through PM100. And then we prorate the boundaries, as I mentioned, into a given frame hour. And then we also do some inference. So the inference is based on a rolling window. 6 hour presently is the configuration of a window. And so for counts that are very low, what it will do is look for a correlation with the overall counts, because particle concentrations tend to co-vary with, for instance, changing wind conditions. And so if it notices a trend, it will essentially try to predict sometimes fractional and low levels for certain particles. And by certain, I just mean those that are very low levels down in what would be noise, to try to get a little more signal. That's really useful, for instance, in fall when you have concentrations of certain particles like ragweed, that even capturing 1 or 2 actually indicates a pretty significantly different outcome as far as misery index and human suffering. And so this allows us to sort of infer down near the noise better concentrations for very low counts. These, though, are kept separate from the actual counts. So we have an inferred count that comes out, and they're going to be largely the same in most cases. But if there's a high correlation and it can infer, then for those certain counts, those will change the numbers a little bit. But again, they're 2 separate numbers. And then we go from counts to concentrations. And I'll talk a little bit more about that conversion and what we do there. And then the net result is a concentration roll-up, as we call them. And the roll-ups are over hour boundaries, over day boundaries, etc., over different rolled up over different time periods. So the overall concentration computation, the density of particles per cubic meter, which is the final output, is based on the particles per minute that we're observing. And again, this is turned into a particles per minute rate, so that it's independent of how long the frame took to sample and how many frames, etc. So that's ultimately all the numbers are distilled into a particles per minute, and then times what would classically be called a conversion factor, which is the cubic meters per sample minute, is how we represent that. And so cubic meters of air per sampling minute. So to dive into that conversion factor a little more deeply, the way we compute this conversion factor is we do 1 over the airflow. So the airflow is in cubic meters per minute. And then we multiply this by a collection efficiency. Collection efficiency is currently configured to 1. A Burckhardt or a rotor-rod, classically the collection efficiency is assumed to be 1. And then you have the proportion of the nozzle to the actual frame. The frame is a portion of that. So the frame is just the area that we're actually measuring on the tape versus the nozzle, which is the overall portion that's exposed to the air. So that's our conversion factor, and that's what's used to convert to a concentration. So next we're going to talk about some coming features. Right now, the way that we roll out new vision models to particular sensors is through something we call dynamic vision. So what it does is we can create these vision model segments internally. If a sensor falls into a given geometric boundary and it falls within the time period of the segment, which is represented as ordinal days from the beginning of the year, we can basically associate it with a given model that we've trained. So we might put a certain set of particles into a given model, train that model, and then we can associate that, and we can associate it with a given usage code like outdoor ambient. And that determines for this particular model, in this case would be pollen, what is going to be used within that time and space. The problem is that you can basically subdivide these, and also as the seasons roll on, then some of these types will drop out and new types will drop in. So there becomes an almost endless amount of subdividing of these segments. So it's very difficult to maintain these and keep them accurate. And then we have to go and manually retrain a model for each of these based on the set of things that we expect to be there. And if we change a model, we have to go back and find all of the segments that are using that. So we have a new system for this dynamic vision system. Instead of this segmenting system, we essentially can represent the overall, we can basically paint and load sources of where we expect a given particle type to be spatially, and we can also specify curves that specify the season or seasons where we expect them to be in time, and the new system will dynamically train a new model for each sensor for each day based on where that sensor is and when that sensor is. It will get its own custom model that fits just right, and we can account for a shoulder to allow for an early season or a late season, etc. So that's going to allow us to provide better quality, less error prone, and also more granularity. So it should improve the overall quality of the vision system and the outgoing analytics. But the other thing it's going to allow us to do is provide a quality control check, because we can look for anomalies. So if a given sensor is reporting a very high level of something where maybe we are not expecting that, or not reporting something where we are expecting it, or if the season comes early, whatever the case may be, we can catch anomalies, and this allows us to raise them as alerts and either deal with them as device issues or as issues with the model. So we're excited about these changes, and we have a lot more things coming. We'll try to keep our customers updated with these things. We appreciate you for being a customer, and thank you for your patience. It hasn't been an entirely smooth rollout of all of these things. We've had some hiccups, so we appreciate your patience, but we will try to keep you informed as we go. Thank you.